Hey everyone, before we get into the video, I just wanted to announce that I finally got around to posting the equation sheet. It will be in the description of every relevant video. In fact, I've already filled in the equation sheet to the previous videos, so go ahead, check that out. It's in the description, like I said. Just download it and you can follow along at home. I will probably be updating the equation sheet throughout time, just as I discover more and more useful equations. But without further ado, let's get into the video. Salutations, Internet. Good time zone. So, last video, I would say, it went alright. It went alright. However, we still have a little bit of a problem, because when we started our example, we started with a position vector and a velocity vector. And why would we want to use anything with Lambert's problem when we can just use this here and then all the rest of the two-body problem? Well, I say that's a great question, and to that I reply that we are not done, because if you remember from our definition at the beginning of the series, we had an initial position, a final position, and a time of flight between them. And also, as I hinted at in the previous video, the Lambert's problem equation set is not complete. We're still missing some stuff. So what do we add to it? Well, the hint is right here. Time of flight. And anytime we hear time of flight, you should be thinking of either the eccentric anomaly equations or the escape trajectory time of flight equations. There is an alternative set that is more universal, but I am electing not to go diving into the universal anomaly angle just yet, because there is a lot that is going into that. And I don't know about you, but having spent, what is this, the 6th video in the air quotes micro series, I'm ready to move on, so I'll come back to that later. Right now, though, we are going to continue with the eccentric anomaly angle. So, really quick, let me set up a diagram. That's enough. So we have the Earth, we have a vacant vertex, and we have the center of the orbit. This distance is a times e. We covered this already in a previous video that I will put a time or a video card for up on the screen probably about now. And these are both distance a. This is all stuff that we've dealt with before, but we're going to reframe it in the perifocal reference frame. So we have, for our radius in the p direction, I'm only going to put the p direction with this, the periaps, it's going to be pointing towards the positive p direction. So we have a minus a e and all of that. Again, in the p direction, nothing in the q direction. I'm not going to bother writing it up. We go in the opposite direction. We have our a, the apoaps, and that is going to be actually minus a times e, because it is, while these two are being added together, they are also pointing in the opposite direction of p, so they get to stay negative. Having done all of this, we can see that our position vector in the p direction is going to be a times the cosine of the eccentric anomaly angle minus a times the eccentricity. That needs to be capital P. And because we're dealing with vectors, we also need to know what's going on in the q direction. I don't need to scroll yet. So we know that the greatest distance here is going to be the semi-minor axis, which is a times the square root of 1 minus e squared. That is then going to make our r vector in the q direction a times the square root of 1 minus e squared times the sine, the eccentric anomaly angle. And for the sake of completeness, I will underline that one as well. Now, hopefully I can find it. But it is not enough to have the radius. We also need to have the velocity. And fortunately, since this is the position vector, we can just take the time derivative of that. So dr dt v, and that will be a times e dot times the sine of e. And because a and e are constants, there's nothing else here. That is in the p direction, not delta, p hat. And then we need to know a sign there. Give me just a second. Yes. Theta. So it had been cosine. As theta increases, cosine decreases by the value of sine, which means that that is a negative. We will then add to it. So that is a constant, a times the square root of 1 minus e squared times e dot times the cosine of e. And similarly, when theta is increasing, sine will increase by the value of cosine, so that stays positive. No, we are not done with that yet, because we need to know what e dot is. And we can derive it ourselves again. I say again because we've already derived it once before. And actually in the video where I derived the semi-minor axis. Fun fact. So scroll down, e dot shows up. E dot is defined right here. So square root of mu by a cubed. Let me write that down. So we have v is equal to minus a times the square root of mu by a cubed. Mu by a cubed times 1 over 1 minus e cosine e. 1 minus e times the cosine of e inverted times sine of e. No, let me back that up a little bit. Let me back that up because so we have e dot here. Let me copy e dot over. So making a note. Scoot down. There we go. I have e dot is equal to the square root of mu by a cubed times 1 minus e cosine e. 1 minus e cosine e inverted. Well, also in this video, let's see if I can find it. I have a better definition There we go. So we use 1 minus e cosine e here, which means that if we solve for this directly, we have r over a. And since that's in the denominator, e dot, hang on 1 second, I need to copy this over. Since that is in the denominator here, so it is not r divided by a, but it is inverted, it is now a divided by r. Okay, a divided by r, that can be simplified down to 1 over r times the square root of mu, times the square root of mu over a. So now we can plug that back into our velocity, which will give us in the p direction minus a times 1 over the square root of a, square root of mu times a over r. That is a and e dot times sine of e, the p hat direction, plus, so similar thing happening over here, where we will have the square root of mu times a times the square root of 1 minus e squared over r times the cosine of e and q hat. All right, and that is our velocity. So give me just 1 second and I will copy down radius here just so that it is all in one place for me. All right, so I have copied over the radius and I got rid of the blue lines because that's going to get in the way. So if you recall from, I believe it was the second video in the micro series, we made a vector with r and v, and we put everything in terms of p hat and q hat. I'm going to do some shorthand here just to make it a little bit faster for me. So we have a, let me write this in a different color so it stands out, a, b, c, and d. So we have a, b, c, and d. So now when we go to invert it, we have p hat q hat times 1 over, oh, I don't remember what the name is. I will probably put it in text off to the side here because I don't remember what this is called, but it's 1 over this, which happens to be the angular momentum, the specific angular momentum, even though we are doing all of our equations in terms of the eccentric anomaly angle, it turns out it is still going to be the specific angular momentum. So that's nice. We will then replace or swap those two. So we'll have D and A, and then we will negate these two. Minus B minus C. R V. Okay. Now our P hat is going to be 1 over H times D, which this whole numerator actually turns out to be H. If we look at our equation sheet, H square root of mu times A square root of 1 minus E squared. So we can just cancel that out. So it becomes 1 over r times the cosine of E. 1 over r, that will actually be r naught, the initial, times the cosine of E naught. Scaled by the r naught vector, plus, now this is minus b. I'm going to put the minus sign inside. So it becomes minus a times the square root of 1 minus e squared by h times the sine of e naught, scaled by the v naught vector. We now will work with q. I'll work to find q hat, which is going to be minus c being already a minus, so we can negate that. Already a minus, so we can negate that. Square root of b times a over r, square root of mu times a over r times h. Remembering that that is the initial r, c times the sine of e naught. Scaled by the r naught vector, plus a. Now a is a times cosine e minus a times e. All of this divided by h. So a by h times the cosine of e naught minus a times e divided by h, scaled by the v naught vector. And just as before, we're going to plug it into our r vector to try to look for our Lagrange coefficients. So r begins with our a quantity, a times cosine e minus a times e, a times the cosine of e. Nope, this is not the initial e value, minus a times e times p. So let me copy that down. Plus the quantity of, let me make that bigger. Oop. Plus, we now need b for this. A times square root of 1 minus e squared sine. A times the square root of 1 minus e squared times the sine of e. Times q, square root, square, hello? Square root of mu times a over r naught times h times the sine of e naught, scaled by r naught, plus a by h times the cosine of e naught minus a times e over h, scaled by v naught. All right. Scroll down here. We're going to, like we did before, put everything in terms of R naught and V naught. So we will have A by R naught times the cosine of E times the cosine of E naught minus A times E over R naught times the cosine of E naught plus, and here we see again an H, square root of mu times A, and square root of 1 minus E squared. So they will all cancel out, leaving us with A by R naught times the sine of E times the sine of E naught. Scaled by R naught plus, and this one's going to be considerably larger. So we will have A, nothing cancels out here, so I have minus A squared times the square root of 1 minus E squared over H times the cosine of E times the sine of E naught plus A squared E square root 1 minus E squared over H sine of E naught plus A squared square root of 1 minus E squared over H. And I run out of room. I'll write it off to the side, it'll be fine. Times the sine of E, lost my spot, times the sine of E, times the cosine of E naught. And then I'm going to bring it back over here. Minus A squared E, it's the square root of 1 minus E squared over H times the sine of E. B naught direction. All right. So once again, everything inside of this first set of brackets is going to be our F. So let me copy that over. We have A by R naught. And actually looking at it, we have every term multiplied by A times R naught. So I'm just going to take that out. We have cosine of E, cosine of E naught minus E times the cosine of E naught plus sine E sine E naught. That I have copied that over, I'm going to scroll down. So we write what we know. A by R naught. All right. Cosine E times cosine E naught. We've seen something similar before. We've seen it over here. In fact, let me move this over to here so I don't have to move this. There we go. So we saw, let's see, it's cosine times cosine, cosine, 1/2 cosine A minus B plus cosine A plus B, 1/2 minus plus plus. So 1/2 it is cosines. So cosine of E minus plus plus minus E naught plus cosine E plus E naught. I'm actually going to take this term out to the end, so I'm going to deal with that last. So now the two signs, 1/2 sine minus plus. That's how I'm remembering it. So cosine of E minus E naught minus cosine of E plus E naught. And then minus E times cosine E naught. Now, be careful. It is really tempting to tab over to here and see that, oh, we used this set of equations before. The cosines will cancel out, and then I'll be left with P over R minus 1. Don't do that. You'll spend 2 weeks looking at your work saying, why is this wrong? Don't ask me how I know. Instead, what we want is, again, here. So if we have, there we go. Let me scroll over here to make this note. So we have R is equal to A times 1 minus E times the cosine of E. And then all we have to do is solve for the eccentricity. All right, there you go. Now we have an E replacement value for both the initial and secondary angles, which we need the initial for this one. So let me write this. So we have 1 minus R naught over A divided by the cosine of E naught times the cosine of E naught. Is my handwriting too big? My handwriting was too big. I'll rewrite it down here. Pay no attention to this. So now we can cancel out our cosines. Now we can cancel out our sums of angles. And we can rewrite our F equation as A by R naught times the cosine of E minus E naught minus 1 plus R naught over A. And remembering that this, well, not remembering. Similarly, now that we've gotten to this point, similarly to what we had in the thetas, the theta set, we defined a delta theta as the difference between the angles. So similarly, we will define this as delta E. And when you've done that, you are going to have an F value of 1 minus A divided by R naught times the quantity of 1 minus the cosine of delta E. To save some time, I'm going to go ahead and give you the other 3 Lagrange coefficients. 1 second. All right, so these are our equation sets. This is our equation set. These are our equations, you know what I mean. So we solved for this one. This one is pretty straightforward when you get to it. It's going to be literally the exact same process as what we have already solved for. This is pretty straightforward. This one is not as straightforward as I had hoped when I first approached this series, but you can see some inspiration here. We are using a delta t here, and then subtracting a majority of the right side here. The only thing that we do not have is an e for this. So I have not been able to solve for g yet. I think that would be a fun exercise. I think that would be an exercise for the viewer to approach later. And now I think this is a great stopping point. We are that much closer to being able to tackle Lambert's problem and having a good solution to it. So on that note, I would like to thank everybody for stopping by.